All right. Okay, it's already captured 4 megabytes. So presumably, yeah, it's going. So let me start with giving some very limited hints about problem 2 in the practice problems. I imagine and hope, anyway, I hope that you all understand why I'm not actually going to give you the answer. If this trick of telling you part of the exam ahead of time is going to be of any use, it would be if you actually do most of the work. But I don't want it to be impossible. So here's how I would approach problem 2, which was about the government that wants low-income families to live in better quality housing. It's all about figuring out how the policies, one at a time, affect the constraint or constraints, plural sometimes, that the family faces. Okay? So let's see what. First of all, part A is pretty straightforward. You have a Cobb Douglas, you maximize it, you have the prices. Okay. So then you discover how much they want to rent and therefore what is the total rent bill. So that's easy. So you do that. You start as a reference with that. Then part B, you go and break it into 3 parts, right? So for the first policy, you have to stop and think. All of these policies, what do they affect? Do they affect the utility function of the family? No. What is the source of any preferences? The person, in this case the family, right? The government can tell you whatever they want, but your preferences are your preferences, right? We're not talking about brainwashing here or any horrible Soviet Union stories that you read in the 1970s. So, part 1, an income subsidy that gives additional income. Think about it and don't overthink these. What is the change in the budget constraint? Do we have a new constraint or do we just modify the budget constraint? Introduce a new variable and call it the amount of the subsidy for, call it whatever you want, but define it and let me know this is the subsidy that is to the income of the family, right? And then resolve the problem with this new version of the budget constraint, right? And discover, okay, you have the first order conditions, right? In those now, that new variable, the income subsidy, will be sitting there as a letter. But everything else is known, including the fact that you want the rent, total rent bill to be, whatever I said, 150, right? From that, you ought to be able to find what is the subsidy in part 1, right? All right, that then you put aside, you figure that out, now you continue to part 2. A price subsidy that pays a percentage of the family's rent. Okay, think hard, but not too hard because it's really simple. What do you do to the constraint? Something has to change, but not the income this time. Change the constraint appropriately, right? Find the first order conditions. Discover what percentage P will make the family desire to spend $150 on rent. And once you find the P, figure out, okay, multiply it by 150, right? And figure out what is the actual subsidy then that the government will end up paying the government in this case. Okay? Part 3, a voucher that pays an amount S towards a family's rent, provided that the normal rent is at least R. And R is going to eventually be 150, obviously, right? So now, here, it is yet still a simple modification to the problem, but you may have to think about a second constraint. how you're going to incorporate the fact that you get the extra money, right? Or maybe a breakage of the constraint, of the original budget constraint, right? So on this one, I'm going to actually do something I didn't want to do, but I just convinced myself now I'm going to do it. So lucky you. I'm going to start graphing what the situation might be. All right? So let's put, is X the rent, the housing?
Yes.
Good. Not that it matters, but I have it in one way in my head, and I don't want to flip it around and confuse myself, given how easy it is to do that on the whiteboard. So you had the constraint to begin with, right? So now we go find R, which is going to be 150, right? If the family were to be anywhere to the left of R, there is no subsidy to their income, no voucher, right? So, up to this point, we follow the original constraint. There is no change to it. The moment it hits R, what happens? What should I do now?
Consume it?
What?
Consume it and receive the
Wait, no, what is my constraint? I need to build the rest of the constraint. The part of it that you see to the right of R is incorrect now because it ignores the voucher. And if you are going to be somewhere to the right of R, you're consuming housing as desired by the government. And so the government comes in and gives you a voucher. How does the constraint look?
It moves, right? Like it moves up.
It moves up. We have a discontinuous constraint. It jumps up. Okay? Now, give a name by how much. Well, you know by how much it goes up, right? It has a letter. We called it S, right? So the constraint is going to go up by S. Okay? Now that was by far the hardest thing in this problem. Now, figure out where is the optimum. So the constraint is, I should sensorily cut out this part. This is the constraint. Go find what is the new optimum now. Again, it will be somehow related to the letter S, right? The variable S.
I'm gonna try to print it.
And then set R to 150, figure out the S. And now you have a way to calculate in 1, 2, and 3 how much the government has to pay. So the rest is just straightforward. What's the cheapest from the point of view of the government that achieves the goal of making the family voluntarily choose 150 rent? And that is really all I'm going to say about it. Okay? All right. There was no other request on Canvas for practice problems, I believe. That was from Madan. Since we're here, if I will take any specific question you might have, rather than how do I do, no. I mean, if you have a specific question on any of the practice problems, okay, that's fine. I've given you enough information on the last problem to start you up. And I believe that problem 1, especially after I corrected my goof at the end, should be straightforward. Okay, you know the definitions, apply the definitions, especially on the exam. Write down everything, tell me, and by this definition, I conclude this. Don't just say calculation, 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 calculation. I want to see what you're saying. You're telling me a story. You're telling me a story with mathematics in it, but it is a story, and it needs to make sense. Things need to follow other things logically, and so on. Most especially on exams, but also in homeworks. In homeworks, I've been very lenient and often just gave full marks, even if you didn't give me the story. That's because I don't want to be too harsh from the beginning of the semester. I'm going to get harsher. So generally speaking, tell me the story. Okay? All right. Okay, so we have two problems, two questions from Luke to discuss. This is, okay, still recording. One was Afriad's theorem, condition 3. What page is that?
133.
Okay. Right. Now, just to make sure I'm answering the right question, you would like me to explain what these inequalities mean?
Yes.
Okay.
Yes, and like the intuition behind them, because like the
Right.
other 4 parts of it are kind of
Yes.
self-explanatory.
Okay. What they mean is related intimately to concavity. There are two ways that you check concavity if the function is differentiable. So let's stick with the differentiable function. One way you're familiar with, I'm pretty sure, if you've done any second-order conditions. You take the Hessian, the matrix of the second-order partial derivatives of the function, and you check to see if it's negative semi-definite. And if it's in fact negative definite, then the function that generated that matrix is, if it's negative definite for all points in the domain, all of those statements for concavity, semi-definite or otherwise, apply to the entire domain. It's not enough to say at this point, because then you're only doing the local. Okay, so if it is negative definite over the entire domain, if the Hessian is, then the function is strictly concave. Right? That is the second order condition for concavity, or test for concavity. But there is a first order one. And that is actually extremely intuitive. Here's a concave function. The graph of the function f might go like this. All right, so take a point. So let's call it x0. It's some point in the domain of definition of the function. Draw the tangent to the graph of the function at that point. Okay? The coordinates are so, right? Now, where is that line? Always above the graph of the function. This is an immediate consequence of the definition of concavity, which is that the subgraph of the function is a convex set. And there is a theorem that says if you have a point, so the subgraph is a convex set, and so is its interior. So if you have a point like x0, f of x0, which is not in the interior, it is separated by at least one hyperplane from the convex set. We didn't really talk about that, but that's the reason. One of the reasons we love concavity. You get this convex set, which is always separated from points outside of it, with at least one hyperplane. In R2, a hyperplane is just a line. In R3, it's going to be a plane, and so on. Always one dimension less than the dimension of the space. Am I making sense geometrically? Yes? Okay. So, the next thing to do is to go look at 8.4 on page 134. So, let me make a little triangle here. I didn't call it xt and xs. So I'm going to keep my notation, and then you'll be able to connect what's in there. Let's take another point. So what if I call this one f1, x1? So f of x1 is here. All right? And let me make a little triangle here. Right? It's supposed to fall exactly on top of the black dotted line, but of course my hand missed. Okay? All right. Now, remember again, what is the whole point of differentiation? Why do we do derivatives? Because they are a local approximation to a function, right? In this particular case, actually, I don't care if that it's local or not. No matter where I chose x1, I know that f of x1 will be below the corresponding point up here. Because the tangent hyperplane, like I said, is everywhere not below the graph of the function, because the function is a concave function. Right? Okay. So then, can I calculate this height? Can I? Little trigonometry maybe? Rise over the run? Well, the run is x1 minus x0. What is the rise and how can I calculate it? Do I know this angle? Yes, you do. What is it?
Is it 45 degrees?
Nope, not necessarily. The function is differentiable, I assumed. Come on, somebody has to be brave to blurt it out. When we take a tangent to the graph of a function, what do we know about the angle it makes?
So,
Yes?
well, we know it's at that point.
Yes,
it's
at
90
that.
degrees.
No.
No.
You can see it's not, for one thing.
Well,
No, not that one, this one.
The slope is the same at that point.
The slope is the same as what?
As the slope? There.
I want the tangent of this angle. Let's call it theta. What does it equal? You all know it from calculus. All right, equals the derivative.
seriously?
Oh.
I keep telling you not to overthink things. Now, if you stand here and sit here, and tell me that you never saw this in calculus class, then I want to go and slap your calculus professor. It probably is back in the mists of history and you forgot about it.
Maybe, but it makes sense.
Yeah!
So I know what
It sure does. Okay, all right, okay. Enough of my comedy. It's not very successful. Now, observe 8.4 again. Is there a derivative at some special point? Yes, du of x star. Aha! What if you put x star, the star? xs, sorry. What if you call xs like the x0 here, and xt the x1? And this inequality becomes then that the red height here is greater than or equal to this black height. This is what 8.4 says, quite literally, but it says it in any number of dimensions. So that's the interpretation. This says, hey, look, 8.4 is direct consequence of concavity, right? It's the first order derivative test for concavity, in fact. as opposed to the second order, which has to do with the Hessian. All right? So that should explain 8.4 fairly well. Right? Just move the uxs to the left-hand side, call the function f. Here's the distance of the f's, and here's multiply the tan, what is tangent? This side divided by that. This is precisely 8.4. So I want you all to figure this out and make sure you understand it. And then Afriad's theorem says, oh, hello, even though I don't know my utility function, right? It follows that I have numbers that look like that. Right? Now this lambda is not written as a derivative, right?
Right.
So that still leaves some room for a connection, an explanation. Okay, so the explanation is what he provides on the next page, where he says, look at the first order conditions in 8.3. Aha! You can then take those and put them in the place of du, and all of a sudden, it connects very tightly to condition 3.
Okay.
Yes? So it's a way of getting approximations,
Okay.
right? It's like you don't have many points, but you have a bunch of S's and T's that you have data, and they're going to tell you, well, from each one of those there shall exist the lambda numbers which then are proportional to the first derivative vector, and so on, or multiplied by the price vector. And you have the price data. Your observations are x points and p points. And that's all I'm going to say about that. Good? Did I think I didn't miss anything crucial. If I did, well, shoot me an email, but I think I'm going to leave it at that. So that's the connection there. Good? All right. What's the other? Recoverability.
Yeah.
Okay.
The pictures just weren't.
Just a
weren't
little
doing
few
it for me.
pages down. 139.
Yeah, 139, and then the
Right.
the graph
Right.
on 140 as well.
I'm going to do 139.
Perfect.
And you're going to do 140 on your own. Okay?
Sounds good.
All right. I view this as very cool, by the way. And here's why. We started talking about preferences by saying you have a set of possible alternatives, so let's call them the goods x1 and x2, as usual here for my pictures. He calls it good 1, good 2. Okay, fine, same thing. And if you remember Rubinstein's book, it said, well, you ask an infinite set of questions, right? Here's a bundle, here's another bundle. Do you think this is better than that? Do you think that is better than this? Do you think they're indifferent? You can phrase the questions different, but you have to cover those possibilities, right? So then if you ask enough questions, you will be able to eventually draw the indifference map, but you need to ask a lot of questions. This takes a different approach and says, let's say you have a finite and possibly small set of observations about, but not just observations about x's. So the questions Rubinstein asks are, here's an x vector, here's another x vector, tell me how you feel about them. Here we have more data, but not much more. You have an x vector, and you have a price vector at which that x vector was actually purchased. And you assume the person is maximizing utility, right? You do Afriad's theorem. So now, from that one piece of information, that xp, what does he call it? x1 and x and p1, right? What can you learn? All right? So we're going to draw a budget line, which corresponds to the prices that you observed, P1, I think, yes. And we're somewhere on that, and I'm putting it more or less where he has it in the book, there is X1, which is what the person actually purchased. Right? Okay. Now comes the really cool part. I'm going to delineate for you an area where the person's indifference curve through x1, or actually through some other point x0, must pass. So here's a point x0. Notice the sequence I'm taking these. I don't know the prices of x0. He makes it very clear in the book. But it's a point. So I'm going to ask myself, can I tell you something reasonably precise about the indifference curve that passes through x0? The answer is yes, I can. Observe, is x0 affordable at a prices p1? Yes. So therefore, x1 has been revealed preferred to x0. Okay? Now, what else has been revealed preferred? Connect x1 to x0. So here, I connected it.
See you on Monday, Jim.
All the points here are revealed preferred to x1 for the same reason that x0 was.
It's going to be a nice one, I hope.
Right?
Wait, can you say that again? All the points on that.
All the
line are
points
revealed.
of this segment are revealed preferred to x1. Well, except x1 itself.
Right. Okay.
All the points in the interior of this are revealed preferred to x1 because they're also affordable
Okay.
under the prices of x1, but they were not purchased.
Okay.
Okay? Okay. So the set of those points that are revealed preferred to x0. Wait a minute. No. These are x1 is revealed preferred to the points here. To the points
okay.
here. The x1
Okay.
is-
That,
See, I do those
thought,
things. And
okay.
yes. Okay. So let's actually start this way. I have nothing about prices for x0. So the price, the vector here, so I'll start with this. The budget through this could have been like that, could have been like this. It would have to be some negatively sloped line, right? Any points that are below the budget line and that passes through x0 have been revealed preferred to x0. Right? If you actually observe x0, right, then from the x0 you know anything that is cheaper for the same reason as before is preferred. I should have started with x0, but anyway, is preferred. X0 is preferred to it. What is the set of points that you know for sure will always be cheaper than x0? Well, if I go horizontally and vertically, all of the points here, no matter what the prices are, as long as the prices are not negative, they're going to be below that budget line, right? No matter what the exact slope of that little red budget line is. So this is the set of points that we already know are revealed preferred. But there's more. Now let's see. Right. If the line connecting x1 to x0 is it's one of the possibilities, right? That could have passed through x0, right? In that case, we know the person would have chosen x1, right? So the points as you go down are less and less well regarded than x1, right? And if you keep going down from x0, these points are revealed preferred to x0. Because if that was the budget line, they would not have been chosen from x0. Now, all the points from x1 to x0 are revealed preferred to x0. Then, if you go vertically above by monotonicity, all of these points are revealed preferred to x1 and therefore to x0 by transitivity. right? And if you go up this way, all the points on that segment are revealed referred to x0 because of monotonicity, if nothing else, right? And now, convince yourself that if you shade this, they're all revealed referred to x0. So this is a revealed preferred set, and this is, I wrote it wrong, I always do that, this is a revealed worse set to x0. So look now, with that argument, we already have limited the room that the indifference curve has to pass through x0 quite a bit. It must pass through the unshaded areas,
Okay.
right? Then the next picture does this with additional information and makes the area more and more precise, more and more narrow. So what is then the word recoverability doing here? The word recoverability is that you're recovering information that's hidden from you, from information about the shape of an indifference curve. Information that you don't have, but you have information about choices at different prices.
Okay.
So you're getting out of that information as much as you can with the additional assumption that the person considers these goods and not bads, and so therefore you give him more and he's happier.
And
So that's the logic here.
And so that's the more like empirical
Yes.
look into
Yes.
finding indifference curves, finding utility.
Yes.
Of that.
Yes. So it answers the question. And criticism, a very pointed criticism of economics, which was, why are you making a theory built on unobservables? I can't go into somebody's head and see their indifference curves. And the answer is, this is Samuelson's answer, basically. Well, if you can observe them at the marketplace, and yes, you can observe them in principle in the marketplace, then you can, with enough observations, you can approximate an indifference curve quite well. And that's really what you're trying to do, to recover this hidden information about the preferences of the consumer.
Okay.
That's all. He has other chapters here that are wonderful. If you're going to do empirical work, I seriously recommend chapter 12, which I didn't put in because it's already overloaded what I'm trying to do. But a lot of you are going to do some empirical work about demand. Chapter 12 is a must then. Just keep that in the back of your mind. I believe I covered everything that was requested. Yes?
Sorry, I have some questions.
Okay.
Well, I'll ask Madden's first. She had another question.
Which one was that? I think I did it.
She didn't post it.
Okay, all right.
I think, if I'm reading this correctly, she has a question for page 185 about, I'm assuming, the differentiation going on there. So for above, so if we start at the first equation and then work our way down. So I'm assuming I'm looking at it, I am a bit confused myself about how we get from the first line to the second line.
Okay. Right.
I'm sure it's just the math.
It's precisely correct. It is just the math. You use the chain rule, differentiating with respect to W, right?
Yeah.
See how A changes as W changes. So take the first, it's an identity, the one 2 lines above where you're looking at. Mm-hmm. That one. The first equation of that page is actually an identity, which justifies taking derivatives on both sides with respect to W.
Right.
The right-hand side is 0, of course, there's no W.
Right.
The left-hand side, the W is in 2 places inside the U prime.
Right.
Right? Mm-hmm. So then what's happening here is the derivative has been taken and the chain rule has been used.
Okay, so the AW, the A prime there is...
Because of it's the inner function, okay. The chain rule.
Whatever that one is. Okay.
Yeah? Okay.
All right. And then, so I feel like Roy's identity is very integral in everything we're doing. And I guess just following the intuition behind it, I understand how if we take the demand and take the derivative with respect to prices, like I understand what that means in terms of taking the expenditure, like taking the second derivative, or not. So you have, okay, Roy's identity is
Ra's
the-
identity.
Raw's identity, sorry, is the demand is equal to essentially you have the indirect utility with respect to prices over the indirect utility with respect to income. The
And
negation of
that's a
them.
negative, yeah.
So that is also equal to the expenditure function when you take the derivative to prices. So how, like I can understand the expenditure function with respect to prices, but how does the indirect utility work out? Or am I like
Okay.
way off?
If anybody can tell
So
me.
I have a page. So
Yeah.
if you go to like page 125 with the integrable, however you say that word.
Integrability. Yeah.
Problems.
Yeah.
So just I guess like it's not like I can do it, that's fine, but I just want to know like how is there an interpretation for that, or is just
Okay. All right. So you're asking about the interpretation of Ra's identity.
yeah, but
Okay.
specifically for this portion of it, like the
Well, I don't
Right,
understand this because 8.1 simply repeats Ra's identity.
yeah,
That's it.
that's it.
So yeah,
And-
it just takes it and uses it and says, "Oh, remember, Ra's identity says this." So the answer to that is, what does Ra's identity mean? Is to look at its proof.
Okay,
That's the best I can give you.
okay.
Um,
I looked at I mean, the proof makes sense to me. I just was wondering whether or not there's like some economic way that I should be looking at it.
well, let's see. We have the derivative with respect to price of the achievable utility,
Yes.
right? And we divide it by the derivative of achievable utility at these prices and income with respect to income,
Okay.
right? So
Maybe not really.
I don't know that I can give you any formulation in words that will make it more intuitive.
Okay. Alright. Well, I'll just
Others are easier, I agree. The
Right.
fact that the Hicksian demand is a derivative of the expenditure function is fairly straightforward from the envelope theorem.
Mhm.
So,
Okay.
all right.
And then I'm having trouble with endowment. Like when we're thinking about endowment and income.
Yeah.
So-
Endowment is a fixed vector of commodities.
Okay.
That's it.
Just
A fixed
treat it as
vector of
such.
commodities. What you come to the table with.
Okay.
So you think of it, you're entering a room and you're going to bargain with people to buy and sell things.
Okay.
You walk in, you have some.
Okay.
That's your endowment. The important thing that the endowment is fixed, it's given, it's exogenous, but the monetary value of it is not exogenous because it depends on the prices, and those are endogenous.
Okay.
Okay?
Okay. And then lastly, on page 155, this is just another like, well, I feel like some of the notation changes a bit, and I don't see how. So if you're looking at equation 9.5,
Yes.
how do we get from the above equation to the one below? So you like everything else. If you're looking at the summation above it, we have a summation in terms of xi's, but this is now in terms of xj's, and for some
okay.
reason I'm failing to recognize how
The I and the J are completely arbitrarily chosen.
Okay.
When you have a summation,
Mhm.
the running index is up to you completely,
Okay.
right?
Yes.
So the reason he puts J down at 9.5
Mhm.
is that he doesn't want to conflict with the I on the left-hand side.
Okay.
Because the J at the bottom of the denominator, that is, of 9.5,
Mhm.
is just a dummy variable.
Okay.
It will never appear when you write out the entire sum. Write out the sum at the bottom. There will not be a J, it will be 1, and then there will be 2, and then dot, 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 and it will be K at the end. So J is a running variable. It's going to disappear.
Okay.
Okay? So in fact, you know what he could have done? He could have called the previous one, well, he's correct, of course, at the very top, the first order condition, right? The first equation.
Yeah.
He could have used as a subscript, choose any letter you want. I don't care. The important thing is for that letter will go from 1 to k. So in that as well, the I is a running variable. It's a for all statement.
Okay.
The I on the left-hand side of 9.5 is not a running variable. Now we're talking about a specific commodity with index I.
Okay.
Okay?
Okay. That makes much more sense. Alright.
All right. All right. Okay. So let me save this.